Have you ever felt the unsettling thrill of looking at a photograph and realizing you don't understand what you're seeing? Imagine for a moment that you're not on Earth. You are floating silently above the rugged canyons of Mars. Under your boots, the ochre dust stretches in every direction, a barren canvas of rocks and scars older than any human civilization. And then, without warning, you notice something that doesn't belong. Across the pale slopes, dark tendrils begin to snake downward, appearing out of nowhere as though an invisible hand were painting them in real time. They twist and lengthen, winding into patterns that resemble rivers or veins, only to fade again after a few weeks as if they were never there. What could create such ephemeral scars on a planet so cold that liquid water shouldn't exist in any familiar form? This is one of the questions that keeps scientists awake at night, and perhaps, if you let yourself imagine it deeply enough, it will keep you awake too. Because these fleeting dark streaks are not just curiosities, they are clues scattered across the Martian surface like cryptic messages. Clues that whisper to us about the possibility of hidden aquifers, salty brines capable of staying fluid under temperatures that would freeze a human in minutes. Or perhaps they're telling a different story, one of fine, dry grains cascading downhill in slow-motion avalanches, released by the daily cycles of sunlight heating the shallow crust. The more we photograph them, the more we realize how little we truly know. For every confident hypothesis, water seeping through porous rock, briny trickles gathering in sheltered gullies, there is a rival idea ready to challenge it. Maybe this is what makes planetary science so electrifying. No matter how many satellites we launch, no matter how many terabytes of data we collect, the surface of Mars remains an unpredictable mosaic of secrets. And we are the ones tasked with deciphering it. Today, we will journey together into these riddles, questioning what we see and daring to ask if our eyes alone can be trusted. We will travel beyond Mars to the Moon, where for decades humanity misread the shadows and bright scars as towering mountain ranges that never existed. We will talk about how the visible side of the Moon, always turned toward us, holds on to more warmth than the far hemisphere that never meets our gaze. And we will visit the Sun, where a colossal silhouette, so immense its wingspan would dwarf our planet, appeared for 10 minutes before melting back into blinding white light. What was it? A glitch in an ancient camera? A stray wisp of matter dancing in solar winds? Or something else entirely? An omen, a reminder that the universe loves its illusions. By the time we reach the end of this exploration, one truth will feel inescapable. When we study the cosmos, we are not simply gathering facts. We are learning how to question the certainty of our own perceptions. We are accepting that sometimes the most beautiful discoveries are those that refuse to fit neatly into any explanation. So take a deep breath, leave behind the comfortable boundaries of Earth, and join me as we set out to trace the shadows, the patterns, and the strange echoes that drift between planets. This is a journey for curious minds, those who find wonder in the questions that have no easy answers. Let's begin with the Martian slopes themselves, the places where these restless streaks are born and vanish again and again, defying our predictions. When the first orbiters sent back images of these patterns, scientists debated whether their eyes were playing tricks. From above, the planet seemed to wear a patchwork of pale dust and darker troughs, as if colossal rivers had once flowed there and left ghostly imprints behind. But these weren't ancient relics frozen in time. They were dynamic. They emerged in the Martian spring, crept down the walls of craters, and gradually faded as the seasons changed. This discovery rewrote our understanding of what a cold desert world could do. We have to ask ourselves, what forces are powerful enough to paint moving trails on such an inhospitable canvas? Is it truly water, some hidden reservoir of salty brine leaking to the surface when the feeble warmth of the sun returns each year? Or is it something less romantic, yet no less fascinating? A slow rearrangement of the Martian soil itself, a cascade of grains released by cycles of heating and chilling. Imagine standing on the rim of a crater the size of a small city. Under the wan red sky, you feel the surface trembling as the dawn spreads its thin light. Perhaps the grains beneath your feet shift just enough to begin a silent slide down the slope. The Martian wind is nearly absent, more a suggestion than a force, yet over weeks and months its occasional gusts can peel back the upper layers of dust, revealing the darker sediments hidden below. To human eyes, it looks so much like the aftermath of a rainfall that even seasoned geologists hesitate. But why do we care so much whether it's water or dry sand? Because water is the elixir of possibility. If briny trickles can endure on the surface, it means Mars still possesses the ingredients to sustain life. Maybe only microbes, maybe nothing more, but even that would be the most momentous discovery in a century. And so every mission, every rover, every high-resolution survey becomes a kind of detective story. We search for the smallest clues, a change in albedo, a trace of minerals left behind, a pattern that repeats in ways no random landslide could mimic. And as we search, we remember that Mars does not reveal itself easily. It gives us just enough evidence to hope, then dares us to prove it. To grasp why these Martian streaks provoke such heated debate, we need to picture how our robotic explorers observe them. Imagine a spacecraft gliding hundreds of kilometers above the rust-red plains. On board, a suite of cameras stares relentlessly downward, capturing the same slopes over and over again. Each photograph is a tiny fragment of a vast mosaic, a freeze frame in a slow-motion performance that has no script. When the Mars Reconnaissance Orbiter first began to monitor these features in earnest, scientists noticed a curious rhythm. In the coldest months, the slopes looked bland, pale, almost uniform. But as the sun climbed higher, thin shadows lengthened, and then, almost like ink soaking into parchment, dark lines began to unfurl across the terrain. At first, they were subtle, a few meters long. Weeks later, they stretched for hundreds of meters, tapering like the delicate roots of a tree. No spacecraft had ever seen anything quite like it. From Earth, we could only speculate. Some researchers argued that thin films of salty water must be percolating up through the soil when the temperature climbed just above a critical threshold. After all, on our own planet, even in the most arid deserts, hidden reservoirs of brine can emerge in unexpected places. Others insisted that the explanation was simpler, if less poetic. Mars was merely shuffling its dusty cloak. As the surface warmed, the loose grains rearranged themselves, exposing older, darker material beneath the sun-bleached crust. But here is where the story becomes stranger and more compelling. As soon as our teams tried to reconcile these observations with what we know about Martian conditions, contradictions emerged. The air pressure is so low that liquid water shouldn't survive more than a few moments before evaporating or freezing solid, and yet the streaks looked uncannily like the aftermath of a slow trickle. We began to consider that maybe our expectations were too Earth-centered. Maybe on Mars the rules are subtly different, enough that tiny amounts of briny moisture can persist, at least for a season, before disappearing again. In the lab, researchers created simulated Martian soils, chilled to frigid temperatures, and added salts like perchlorates that lower the freezing point of water. To their astonishment, small droplets did form, clinging to grains of sand for hours at a time. And so the debate remains alive today, unresolved and provocative. Each new orbiter brings sharper images, each rover sends back mineral data, and every time we think we are close to certainty, Mars reminds us that certainty is a luxury it does not grant easily. Yet even in this ambiguity, there is a quiet thrill. Because every dark streak, every ambiguous trace is an invitation, a reminder that the universe is richer and far stranger than any tidy theory we try to impose upon it. To truly appreciate why these Martian flows captivate us, we have to ask ourselves something simple. Why does the idea of water on Mars strike such a powerful chord in the imagination? After all, the planet is a wasteland, colder than Antarctica, thinner in atmosphere than any mountaintop on Earth, bombarded by ultraviolet radiation strong enough to sterilize its surface within hours. And yet, we keep returning to the hope that somewhere beneath the dust, liquid water might persist. Because water is more than a molecule, it is a promise that life is not unique to Earth, that biology can emerge wherever the conditions allow, and that we, as explorers, stand on the verge of discovering something that would shatter the loneliness of our existence. Picture, for a moment, how the first human beings to set foot on Mars might react if they encountered one of these dark streaks. The thin wind hissing against their helmets, the horizon unbroken except for the jagged lip of a crater, and there, in the ochre soil, a trail of darkness curving downhill. They would have trained for years to recognize geological processes, but in that moment they would feel a different sensation, the primal excitement of possibility. Because a living planet leaves marks. It reshapes itself in cycles. It betrays its secrets in stains and rivulets and shifting dunes. And Mars, in its own austere way, is telling us that it is still evolving. We can see that evolution not only in these seasonal flows, but also in the way the dust behaves. Mars is a world sculpted by storms so vast that they can encircle the entire globe for months. When those tempests settle, they leave behind delicate filaments and splotches, patterns that to human perception can look like art or evidence of purpose. In some ways, the planet is an enormous canvas, brushed by invisible forces we only partially understand. And here is the paradox. The closer we look, the more we must admit that our own expectations shape what we think we see. When a researcher examines a fresh orbital image, they bring with them years of training, and also their hopes, their biases, the stories they have absorbed about where life should be found. That's why every new photograph is both a revelation and a test of humility. Even today, with all our spacecraft and computer models, we cannot say definitively whether water is involved. The argument has split planetary scientists into camps. Some hold that brines, transient and elusive, must explain these recurring flows because no purely dry process quite reproduces their uniform appearance. Others believe the simpler answer is the correct one, that under Martian gravity, dust itself can mimic the shape of rivulets, provided the slope is steep enough and the grains small enough to behave almost like a liquid. But perhaps the most unsettling possibility is that both explanations are partly true, and that Mars, like so many worlds, refuses to be defined by any single narrative. In the quiet laboratories where researchers simulate Martian soil, you can almost feel this tension. A tiny pile of grains shifts under artificial sunlight. A bead of brine creeps across the chilled sand. Cameras capture every movement. And in those few millimeters of testbed, the drama of an entire planet plays out in miniature. So, when we look up at the images, when we trace those dark lines across the Martian slopes, we are not only studying geology, we are searching for the outlines of our own curiosity, our longing to be part of something larger, more ancient, and more mysterious than any story we have yet told ourselves. And yet, even as our imaginations drift across the Martian plains, we find ourselves pulled back toward a more fundamental question. How do we know what we think we know when all we have are images and instruments? No explorer has ever stood there in person to watch the streaks emerge. No human hand has brushed against the soil as it rearranges itself. Our entire understanding depends on sensors, on cameras that capture a thin slice of reality filtered through their lenses, and on the models we build in an attempt to reconstruct what actually happens in that alien environment. It's humbling to realize that a vast planetary drama unfolds unobserved, indifferent to whether anyone is watching. On Earth, we can touch, dig, sample, measure with our own bodies. On Mars, we rely on robotic intermediaries, our patient scouts crawling across the regolith, their wheels scarring the dust, their instruments sampling the air for chemical hints. Sometimes, even our most sophisticated machines return ambiguous evidence. Take, for example, the case of the salt-loving compounds called perchlorates. Years ago, the Phoenix lander dug into Martian soil and discovered that these salts were abundant, more abundant perhaps than we expected. They lower the freezing point of water so dramatically that even at temperatures far below zero, thin films of brine could in principle remain liquid. For a time, this finding ignited optimism. Perhaps those recurring slope lineae, the technical name for the dark streaks, really were briny trickles. But optimism in planetary science is always tempered by caution. Later experiments suggested that perchlorate-rich soils could also produce flows without any liquid phase at all. Subtle sublimation, the transition of ice directly into vapor, might destabilize grains and cause dry avalanches that mimic the graceful arcs of flowing water. We are left with two equally plausible scenarios. The soil might be wet, but only briefly, or it might never be wet at all. Each new observation can be read in multiple ways. A chemical signature here, a color gradient there. Every clue carries the weight of conflicting interpretations. And still, we keep searching, because the stakes are too high to look away. If Mars has even transient liquid water, then the possibility of microbial life moves from speculation into serious probability. In a universe that appears overwhelmingly hostile to life, that is an idea that reshapes our sense of belonging. Imagine what it would mean to wake up to a headline announcing that briny rivulets were confirmed to be wet, not dry. That under the thin Martian sky, a chemical oasis exists in the shadowed slopes, enduring the freeze by the grace of salt. It would be the closest thing to finding an echo of Earth, a fragile, tenacious reminder that biology is not confined to one small blue dot. And perhaps that is why, despite the ambiguities, despite the endless debates in conference halls and laboratories, we feel such an emotional charge when we look at those photos. They are not only records of geology, they are glimpses of what might be. And in those possibilities, we glimpse ourselves, the species that yearns to discover we are not alone. As our curiosity drifts away from the red landscapes of Mars, it inevitably finds a new anchor in the luminous face of the Moon, a companion that has shared our sky for all of human history. When we lift our eyes on a clear night and see that familiar disk, we may forget how many centuries it took to understand what we were actually seeing. For much of human existence, the Moon was nothing more than a pale, unreachable ornament. Its bright regions were interpreted as continents, its dark patches as oceans. Even its subtle color variations were the subject of speculation and myth. But the real revolution began when we sent cameras, not just telescopes, to look more closely. In the late 1950s, when the first Soviet spacecraft photographed the far side of the Moon, hidden from Earth by the Moon's perpetual rotation, those images triggered an intellectual earthquake. Suddenly, we had to accept that half of our nearest neighbor was a stranger, utterly different in character from the side we'd watched for millennia. Imagine the astonishment of the scientists in that era, unrolling freshly developed photographic film and seeing features no human eye had ever glimpsed. A landscape of vast craters, highlands streaked with ejecta, and oddly uniform plains. The far side of the Moon lacked the familiar dark Maria, the basaltic seas that make the near side look like a mottled face. Instead, it appeared rugged, ancient, and surprisingly bright. In those blurry, grainy images, researchers thought they recognized mountain ranges, ridges, and valleys. A pale band stretched across one quadrant of the globe, and in the excitement of discovery, it was labeled the Soviet Ridge, a symbolic tribute to the nation that had captured the first glimpse of lunar anonymity. For years, this feature appeared on globes, maps, and educational posters, enshrined as a real geologic formation. But here is where the story becomes a parable about the limits of perception. Decades later, when high-resolution cameras orbited the moon and returned clear photographs, the ridge was revealed to be nothing more than an optical illusion, an artifact of albedo, the moon's habit of reflecting sunlight unevenly across its terrain. What had looked like a towering rise was merely the bright ejecta of fresh craters spread in a thin sheet across older ground. The ridge had never existed at all. We might smile at this error now, confident in our superior technology. But the truth is that illusions like this are an unavoidable hazard whenever we study alien worlds. Our brains crave patterns, our eyes find familiar shapes in random contrasts, ridges where there are only streaks, riverbeds where there are only shadows, even faces in the craters and hills. It is humbling to realize that even our most precise instruments cannot fully shield us from the bias of interpretation. Whether we are looking at Mars or the moon, we must always remember that a photograph is not reality. It is a conversation between light sensor and human imagination. And sometimes the conversation invents things that are simply not there. But does that make the discovery any less important? Perhaps not. Because every misinterpretation teaches us something vital about how we see, about how knowledge grows through trial, error, and correction. The moon's phantom ridge was a necessary mistake, a reminder that even when we think we have mapped every detail, there are still surprises waiting to humble us. So, the next time you look up at the moon and trace its familiar outlines, consider what is hidden beneath the surface and what illusions still linger, waiting for the right light to reveal or dissolve them. When we consider how the moon has confounded us with illusions and surprises, we're drawn inevitably to an even deeper mystery, one that hides not in the patterns we see on the surface, but in the invisible forces that shape the entire body of our only natural satellite. Because the moon is not merely a passive, lifeless rock drifting in Earth's gravitational embrace, it is a world that once seethed with heat, a world that still holds secrets in its silent crust. One of the most astonishing realizations of modern lunar science is that the moon is not uniform. It is not, as early astronomers once assumed, a perfectly balanced sphere of rock cooled to the same degree in all directions. Instead, the moon is profoundly lopsided, thermally, structurally, even gravitationally. You might be surprised to learn that the hemisphere facing us every night, the familiar side with its broad, dark plains and bright highlands, is warmer than the hidden hemisphere turned perpetually away. But why? Why would one face of a supposedly inert body retain more heat across billions of years? The answer, as so often in planetary science, begins in the distant past, when the Earth was still a molten world radiating immense energy into space. Back then, the moon was much closer, perhaps twice as near as it is today. Imagine looking up at the night sky to see a moon so large it dominated the heavens, bathing the Earth in reflected light and, more subtly, in warmth. In those formative eons, the moon's near side absorbed not only solar energy, but also Earth's intense infrared radiation. While both hemispheres slowly cooled from their own internal heat, the hemisphere facing us did so more slowly. Over time, this difference in heat flow created consequences that still echo through lunar geology. As the crust solidified, radioactive elements like uranium and thorium, elements that produce heat through their slow decay, tended to remain longer in the regions that were warmer. They migrated, ever so gradually, toward the hemisphere most exposed to Earth's glow. And so, the near-side crust became subtly enriched with radioactive isotopes, which continued to release heat long after the moon had largely solidified. Even today, that process has not entirely ended. Instruments placed on the moon's surface have measured the faint trickle of geothermal warmth leaking into space. The difference is small, just a fraction of a degree, but over billions of years, even slight asymmetry can create dramatic effects. But thermal imbalance is only part of the story. The moon is also gravitationally unbalanced. When spacecraft orbit at low altitudes, their paths are tugged upward and downward by hidden masses beneath the surface, regions of denser rock called mascons. These mass concentrations lurk below many of the giant basins on the near side, leftover scars from ancient impacts that filled with basalt and became the Maria we see so clearly with the naked eye. To early lunar navigators, these mascons were a dangerous puzzle. Satellites meant to orbit the moon in smooth paths instead found their trajectories drifting unpredictably, pulled off course by invisible lumps of gravity. The challenge of predicting these variations became one of the first great triumphs of planetary geodesy, the science of mapping a world's hidden gravitational contours. Yet perhaps the most poetic dimension of this imbalance is the tidal relationship itself. The moon does not simply orbit Earth as a passive companion. It is locked into a dynamic dance. Earth's gravity has pulled the moon's body into a slight bulge, elongating it in our direction. Over millions of years, the interaction of that bulge with the moon's motion drained rotational energy, slowing its spin until the same face always pointed toward Earth. Even now, the moon flexes under our gravitational pull. As its elliptical orbit carries it slightly closer and farther, the tidal bulge shifts. The surface lifts and settles by centimeters, motions so subtle they would be imperceptible to the eye, but detectable by the delicate instruments we have left behind. This quiet flexing, this almost imperceptible breathing, is a reminder that nothing in the cosmos is truly static. Even the moon, cold and silent though it appears, responds to the tug of our shared history, shaped by forces that began before life itself emerged on our planet. And so, when we look up at the bright lunar disk, we are not merely seeing a fossil of the early solar system. We are witnessing a world that still, in its own restrained way, remembers the heat of its birth and the gravity of its lifelong companion. If you think about it, the moon is more than a satellite. It is a mirror reflecting our own curiosity. For thousands of years, we watched it shift from crescent to full, believing it to be perfect and immutable. But with each new mission, each layer of measurement, we discover not perfection, but complexity. A body marked by violence, shaped by heat, and still quietly evolving in ways that defy our assumptions. Consider, for example, the invisible tides beneath the lunar crust. Though we imagine the moon as a place of absolute stillness, it is actually in slow, perpetual motion. The tidal forces exerted by Earth don't only deform the moon's surface, they also squeeze and stretch its interior, creating stress fractures and driving subtle flows of rock and heat. You might think this internal flexing is trivial. What difference can a few centimeters of movement make over billions of years? Yet in planetary geology, even the smallest mechanical stresses accumulate into consequences we can measure. When Apollo astronauts left seismometers on the near side, those instruments revealed that the moon is seismically active. Not in the way Earth is, with continent-shifting earthquakes, but through a constant background of creaks and pops, so-called moonquakes triggered by tidal strain and the slow cooling of the interior. Some of these moonquakes were strong enough to startle mission planners. For minutes at a time, the ground would vibrate, ringing like a bell struck by an invisible hand. And here is where the moon reveals one of its stranger qualities. Because it is so dry and lacks the water-saturated rocks of Earth, seismic energy doesn't dissipate quickly. Instead, vibrations reverberate through the crust far longer, echoing off layers of rock and fracture. A quake that might last a few seconds here on Earth can continue for 10 minutes or more on the moon, a haunting resonance in the silence. It's almost poetic. This sense that the moon is listening to itself, replaying the memory of every impact and every subtle tidal shift. When we left our instruments behind to measure these tremors, we weren't just studying geology. We were eavesdropping on a world recounting its long, violent story in vibrations too faint for our ears. Even today, after half a century, our knowledge of the moon's deep interior remains incomplete. We know there is a crust, a mantle, and perhaps a small, partially molten core, but in truth, these divisions are inferred from remote sensing and seismic signals, not from direct observation. We have never drilled deeper than a few meters into the regolith. Our understanding of the deeper layers is still a blend of data and educated guesswork. And yet, what we have learned is enough to feel the grandeur of the puzzle. Because the moon is not a cold relic, but a record of the solar system's entire adolescence. Every mascon, every hidden concentration of dense rock, every fracture beneath the plains of the near side speaks of an origin tied to Earth itself. Think about it. The most widely accepted theory holds that the moon was born from an impact so violent it reshaped our planet. When a Mars-sized body slammed into the early Earth, debris was flung into orbit, coalescing into the companion that has followed us ever since. The moon is, in that sense, both a child of Earth and a witness to all that followed. 4.5 billion years of cooling, collision, and slow drift away from us, centimeter by centimeter. And when we look up at it today, when we trace its bright and dark plains, we are looking at a monument to that shared history. A silent partner whose tides still sculpt our oceans, whose pale light inspired the first calendars, whose face has become an unchanging backdrop to every story our species has told about the night sky. And just when we start to believe we have measured every facet of the moon, its tides, its temperature, its subtle quakes, something new arrives to remind us how much remains invisible. In recent decades, a pair of small spacecraft unlocked perhaps the most intimate portrait of lunar gravity we have ever assembled. You might never have heard their names, but they were called GRAIL, short for Gravity Recovery and Interior Laboratory, and their mission was elegant in its simplicity, to follow each other around the moon, measuring their mutual distance with exquisite precision. Picture this: two spacecraft orbiting in tandem, separated by just a few hundred kilometers, connected by a radar beam so accurate it could detect a change in separation smaller than the width of a human hair. As they flew over regions of stronger gravity, those hidden mascons buried beneath basalt plains, the leading probe would accelerate first, pulled forward by the extra mass, while the trailing probe lagged behind. A moment later, the trailing probe felt the same tug, catching up again. These tiny variations in speed were translated into a gravitational map so detailed it surprised even the mission's designers. And what did that map reveal? That the moon is a patchwork of scars and hidden lumps, its gravity as lumpy and irregular as its cratered surface. Under the familiar Maria, the dark plains visible from Earth, vast concentrations of denser rock lurk, leftovers of ancient impacts that punched holes in the crust and filled them with molten basalt. The smooth appearance of those plains hides a chaotic interior. But the GRAIL mission did more than confirm what we suspected. It also taught us that the moon is not a solid, homogeneous body, but a place still subtly shifting, still expressing the aftermath of its turbulent birth. As Earth's tides stretch the moon's figure, those deep masses respond, creating minute shifts in gravitational pull. It is a dance so slow that human senses could never detect it unaided, but there it is, playing out year after year, cycle after cycle. We might ask why this matters. Why do we spend years tracking the wobbles and lumps in lunar gravity? The answer is that each hidden layer is a record of time. It's a fossil, a remnant of processes that shaped not only the moon, but also Earth itself. To understand the moon's interior is to look backward across billions of years and glimpse the final chapters of planetary formation. And there is something humbling about this realization, that the moon is not an inert relic, but a dynamic world, still revealing its story to those patient enough to listen. Even now, we have not explored its far side in detail. We have never drilled beneath the regolith to touch the mantle. We have only just begun to record the seismic murmurs of the hemisphere that never turns toward Earth. This unfinished business is what calls scientists and dreamers alike back to lunar exploration. Because the moon is the closest piece of the solar system's deep history, a place where the evidence has not been erased by tectonic plates or oceans or thick atmosphere. It is a laboratory in the sky, preserved in near-perfect clarity. So when you look up at that familiar disk, you can be sure of one thing. There are still questions waiting in its hidden depths, questions we may not even know how to ask yet. And that, more than any single discovery, is what makes the moon so endlessly compelling. While the moon pulls our imagination with its pale face and hidden depths, there is another realm of the solar system that feels even more elusive, one so blinding in its brilliance that we can never observe it directly with unprotected eyes. The sun, our star, the engine of all life on Earth, is not simply a colossal sphere of fusion. It is a living laboratory of forces we are only beginning to understand. To look at the sun is to look at an abyss of energy. Every second it emits more power than humanity has used in all our history. And yet, for all its familiarity, the sun conceals more mysteries than any other object in our sky. It is not simply a uniform ball of gas. It is a cauldron of storms, flares, and magnetic fields that twist and snap with an intensity impossible to replicate on Earth. This is why, decades ago, scientists designed a spacecraft with a singular purpose: to observe the sun continuously, without the veil of Earth's atmosphere. This mission, called SOHO, the Solar and Heliospheric Observatory, was stationed in a special gravitational pocket known as Lagrange Point 1. There, 1.5 million kilometers from our planet, it maintains a perfect vantage point, locked between Earth's pull and the sun's overpowering gravity. For more than 25 years, SOHO has stared unblinking at the sun's turbulent face. It has watched loops of plasma arch thousands of kilometers above the solar surface. It has tracked titanic eruptions, coronal mass ejections that fling billions of tons of charged particles into interplanetary space, sometimes toward us. These eruptions can disrupt satellites, scramble power grids, and paint auroras across the poles. But even with all this data, terabytes of images and measurements, SOHO still delivers surprises that defy easy explanation. Perhaps the most haunting of these appeared in a single photograph, an image that, at first glance, seemed ordinary, just another snapshot of the sun's halo captured in visible light. Then, someone noticed it. A shape drifting across the field of view, silhouetted against the solar corona. It resembled something impossible. A vast bird, wings spread in silent flight. If this shape were real and located near the sun itself, its wingspan would have stretched more than 100,000 kilometers. For a moment, everyone who looked at the image felt the same instinctive shiver. What is that? A camera glitch? A stray cosmic ray striking the sensor? Or could it be a fragment of matter hurled outward, caught mid-expansion by sheer coincidence? Scientists, being careful, proposed several plausible explanations. Some noted that SOHO's cameras were built with decades-old technology. A bright cosmic particle striking the CCD at just the right angle could create an artifact. Others speculated it might be a transient feature of the corona itself, a hot, dense filament briefly erupting into visibility. Yet there was no consensus. The image was unique. In the frames taken 10 minutes before and after, the shape was gone. It appeared and vanished as quickly as a heartbeat. When you think about it, this is one of the most humbling lessons space science teaches us. Even in the age of relentless surveillance, with satellites circling every planet, We cannot capture everything. Some phenomena are too brief, too subtle, too rare. They remind us that the cosmos is not an archive of static facts, but an ever-shifting landscape of events, many of which we glimpse only by chance. Perhaps that is why so many people were captivated by the image of the bird, not because it proved anything extraordinary, but because it offered a glimpse of how much remains beyond our grasp. It asked us, for a moment, to feel wonder instead of certainty. And if you look up into the bright sky and imagine that colossal silhouette drifting across the sun's face, you might sense what every solar physicist knows in their bones. The more we learn, the more vivid our ignorance becomes. You might think that an enigma like the bird over the sun is a rare exception, a one-time glitch, a curiosity to be filed away. But in truth, it is part of a much larger pattern. Because every time we point our instruments toward the sun, we confront the limits of what technology can capture and the mind can comprehend. Consider how the sun's outer atmosphere, called the corona, behaves. If you have ever seen a total solar eclipse, you know how it looks. A pale halo of ghostly streamers spreading millions of kilometers into space. What's less obvious is that the corona is far hotter than the sun's visible surface. While the photosphere, what our eyes perceive as the surface, hovers around 5,500 degrees Celsius, the corona burns at more than 1,000,000 degrees. This is an absurd fact. It defies common sense. You would expect that moving away from the source of heat should make things cooler, and yet the opposite is true. For decades, scientists have debated why. The leading ideas involve magnetic fields that snap and reconnect, unleashing energy in unpredictable bursts. But no single model has fully explained this inversion of temperature. This is why spacecraft like SOHO and its successors, like the Parker Solar Probe, are so important. They are not just telescopes. They are emissaries sent to record the sun's moods, to measure its wind, to taste its particles, and to help us see how our star is more alive than we ever imagined. And the mysteries don't stop there. Every few days, the sun hurls out coronal mass ejections, colossal plumes of plasma that can envelop entire planets. When those eruptions are directed toward Earth, they can trigger geomagnetic storms capable of knocking out satellites and disrupting navigation systems. To most of us on the surface, such storms remain invisible. But to the spacecraft orbiting high above and to the sensors at the poles, they are as real as a hurricane. We have become so accustomed to the sun's constancy that we forget how dynamic it is. But when you look at the time-lapse sequences sent back by SOHO, you see the truth. Filaments snake and writhe across the disk. Sunspots boil up like bruises and then fade. Loops of plasma snap open and fling matter into the void. And sometimes, for a handful of frames, something appears that no one can explain. A silhouette, a surge, a filament that doesn't match any known pattern. This is what makes the bird image so compelling. It was a tiny window into a universe that still refuses to become routine, even after decades of continuous observation. Because the sun is not merely an object to be studied, it is an environment, an immense, unpredictable system whose smallest fluctuations can change the conditions on Earth in hours. And perhaps this is the most humbling perspective of all. Here, on our small blue planet, we tend to think of ourselves as secure and insulated, separated by the vastness of space from any real danger. But in truth, we live in the thin, protective bubble of our atmosphere and magnetic field. On the cosmic scale, that bubble is fragile. All it takes is one well-aimed eruption, a solar storm many times larger than any we have recorded, to test the resilience of everything we have built. The sun gives us warmth, light, and life itself. But it also reminds us that nothing in the universe is ever fully under our control. The same star that nourishes us can, in an instant, remind us of our vulnerability. And every strange image, Every fleeting shadow that drifts across the corona whispers the same lesson. The cosmos is not here to reassure us. It is here to astonish us. If the sun humbles us by sheer scale and power, it also inspires a deeper question. How do we, as a species bound to a single small planet, even begin to understand such an overwhelming presence? The answer lies in the slow accumulation of curiosity, discipline, and invention. Generations of observers who refuse to accept the sun as merely a blinding circle in the sky. Consider how long it took us to realize that the sun is a star. For most of human history, people believed it was a unique phenomenon, a lamp hung in the firmament, separate from the tiny points of light that appeared each night. It was only when physicists began to dissect its spectrum and measure its parallax that we understood. The sun is not singular. It is typical. An ordinary yellow star, one of hundreds of billions in our galaxy alone. This revelation did something profound. It shifted our sense of place. If the sun is a star like any other, then the Earth is not the center of creation, but a single orbiting world among countless possibilities. For some, this realization was exhilarating, a promise that the universe teems with planets, perhaps with life. For others, it was unsettling, even frightening, to imagine that our existence might be unremarkable on the cosmic scale. And yet, from this vantage point of cosmic humility, something remarkable emerged. A shared determination to learn. We built observatories on mountaintops and in deserts, launched telescopes beyond the atmosphere, and eventually dispatched spacecraft to orbit the sun itself. Each mission brought us closer to understanding how this star shapes our lives. Today, we monitor the sun's every flicker. Networks of satellites orbit Earth, watching for the earliest signs of a solar eruption. Radio telescopes listen to the crackle of charged particles racing toward us at nearly the speed of light. And when a flare explodes, we can track it across millions of kilometers of empty space, predicting when and where it will collide with our magnetosphere. But no matter how sophisticated our instruments become, there remains something primal about our relationship to the sun. Step outside on a clear day, close your eyes, and feel its warmth on your skin. That sensation is a direct link to nuclear reactions occurring in the sun's core, reactions that began before our species existed and will continue long after we are gone. The photons warming your face were born in a fusion furnace 150 million kilometers away, took tens of thousands of years to reach the sun's surface, and then 8 minutes to cross the vacuum to Earth. When you think about it this way, the familiar becomes strange again. The daylight we take for granted is ancient. Each sunbeam is an emissary from the heart of a star that sustains us while reminding us how precarious life really is. And perhaps this is why even the simplest solar observations can feel so profound. Because when we study the sun, we are studying the conditions of our own survival. We are tracing the story of a star whose moods can nurture or endanger us. And in those moments when an unexplained shape, like the bird in the Soho images, appears in the corona, we are reminded that no matter how much we measure, we do not yet know everything. We stand in a perpetual tension between knowledge and wonder, between the certainties we have earned and the mysteries that remain. And if you ask any astronomer why they keep looking up year after year, decade after decade, you will hear some version of the same answer. Because the sun has not finished telling its story. Because there is always something new in its. As we step back from the blinding brilliance of the sun, it's almost a relief to turn our attention to something more intimate, something that lets us imagine ourselves there, touching it, exploring it firsthand. Because for all the awe the sun commands, there is something uniquely compelling about Mars, the red planet, where our machines have become our avatars, rolling patiently across the dust to capture glimpses of a world that feels both alien and oddly familiar. In the past few decades, Mars has transformed in our collective imagination. Once it was little more than a reddish dot, a canvas for fantasies about canals and civilizations. Then, as probes began sending home images, the myth gave way to something far more intriguing, a real dynamic planet, a place with seasons, dust storms, polar ice, and geological scars that hint at a time when water flowed freely across its plains. And today, thanks to a growing fleet of orbiters and rovers, Mars is the most thoroughly mapped body in the solar system after the Earth and Moon. We have cataloged craters and volcanoes, traced the paths of ancient rivers, and drilled into rocks that haven't seen the sun in billions of years. Yet for all this data, Mars still guards its secrets. Think about what it means that a single rover, Perseverance, can spend an entire Martian year exploring a single crater. Imagine the patience it takes to drive a few meters at a time, stopping to scan the terrain with lasers, microscopes, and spectrometers. Each grain of sand is a clue. Each outcrop of layered rock is a page in the planet's unwritten history. And what do we find when we read those pages? Evidence of catastrophe and transformation. River deltas frozen in stone. The mineral fingerprints of long evaporated lakes. Complex salts that could have preserved water in liquid form even as the atmosphere thinned and temperatures plummeted. Yet even more powerful than the science is the feeling these missions inspire, the quiet thrill of knowing that right now, on another planet, our machines are working tirelessly on our behalf. They are our eyes and hands on a world we have never walked upon, reaching out across millions of kilometers to gather knowledge that no human has ever directly experienced. It is almost spiritual, this idea that we can extend our senses across space, that a robot can take a photograph of the horizon at dawn, and that photograph can spark wonder in a child looking at it on a screen. That the simple act of rolling across dust can deepen our understanding of how planets evolve, and even whether life might arise under the right conditions. And sometimes in the middle of these meticulous surveys, something unexpected happens. A gust of wind that wipes the dust from a solar panel, a flash of light that no one can explain, or the moment when a rover turns its camera back toward itself and captures the most improbable image of all, a robot's selfie, standing alone under a pinkish sky. These self-portraits are more than technical accomplishments. They are quiet declarations. We were here. We dared to leave our world behind, if only in proxy. We chose to look outward rather than inward, to ask questions that may take generations to answer. In those images, you can see the reflection of our own curiosity, and you can sense how much more there is to discover. How many layers of mystery lie just below the surface, waiting for the... As much as we marvel at the photographs sent back by Mars rovers, those sweeping panoramas of empty plains, the delicate textures of rocks weathered by eons, there is something especially human about the desire to see ourselves reflected in these distant landscapes. Perhaps that's why the phenomenon of the Mars selfie has become so iconic. It's a simple concept. A rover extends a robotic arm tipped with a camera, aims it back at its own body, and snaps a portrait. But that simplicity belies what it represents, because in that image we see not just a machine crouched on alien soil. We see the culmination of centuries of ambition, frustration, discovery, and perseverance. Think about how improbable this is. A species that once navigated by starlight alone now builds interplanetary laboratories, guides them through 6 months of travel across tens of millions of kilometers, lowers them by crane into an ancient crater, and then commands them to turn around and take a picture. A picture meant not for science, but for us, for the billions of people who will never set foot there, but who nonetheless ache to feel a sense of belonging on another world. When Perseverance or Curiosity sends back a selfie, we can study every rivet and strut in the chassis, every trace of dust accumulated from weeks of exploration. We can see the tracks etched in the regolith, the shadows cast by the arm holding the camera. And in those details, the abstraction of space travel becomes concrete. This is no longer a remote mission controlled by distant engineers. It is something tangible and immediate, as intimate as a photograph from a family trip. But there is more to it than sentiment. These self-portraits also serve a purpose. By documenting the condition of the rover, its wheels, its instruments, the wear on its surfaces, engineers can assess how it is aging under the relentless Martian environment. Every bolt is a potential failure point. Every layer of dust is a clue about how the thin atmosphere carries particles across the plains. Each image is both a postcard and a diagnostic report. Still, it is impossible to look at these photos without feeling the echo of a deeper longing. Because they remind us that for now, our exploration of Mars is mediated through proxies. Machines go where we cannot yet follow. They are our stand-ins, our patient scouts, preparing the way for some future when the photographs will be taken by human hands. And when that day comes, when astronauts finally step onto the ochre surface, when they look up at the pale blue dot of Earth suspended in the sky, they will become the continuation of a story that began long before any of us were born. A story written in every probe, every rover, every telescope, and every risk we have taken to learn something new. Until then, the selfies are more than enough to remind us that we are explorers by nature, that we cannot help but look back over our shoulder and record the proof that we were there, even if only through the eyes of a robot. And if you have ever felt a twinge of recognition when you see one of these images, if you have ever whispered to yourself, "That's us," then you already understand why we keep sending cameras to Mars. Not just to study the planet, but to remind ourselves of who we are and how far we are willing to go to satisfy our curiosity. If the selfies on Mars reveal something profound about our hunger to leave a trace, then so do the quieter stories hidden in the data those rovers collect. Because beyond the photographs and the panoramas, every mission is really a search for patterns, clues etched in rock and dust that might answer the oldest question of all. Are we alone? It is a question that has haunted humanity since the first time we looked up at the stars. We have invented myths and philosophies to fill the silence. We have imagined civilizations on Mars, canals irrigating deserts, towers rising from the plains. And when the first close-up images revealed only emptiness, no cities, no canals, some people felt a kind of grief, as if the planet had let us down. But that was never the end of the story. Because while no advanced beings waited for us on Mars, the planet still holds secrets that could be even more momentous. Instead of fossils of great empires, we search for the chemical whispers of microbes. Instead of ruins, we look for the tiniest hints of metabolism locked in the mineral record. And in many ways, this is a more humbling, more intimate search, a quest to find life not as we imagine it in fiction, but as it might really persist on a world that has grown cold and dry. Consider what it would mean to find such evidence, a pattern of organic molecules that cannot be explained by chemistry alone, or isotopic ratios that hint at biological processes. In that instant, everything we thought we knew about life would expand. We would no longer be the only example. The idea that biology can emerge wherever conditions allow would shift from theory to reality. This is why every gram of Martian soil matters. Every drill core extracted by a rover, every rock vaporized by a laser, every trace gas measured by an orbiter, each data point is a chance to catch the faint signal of something alive. And yet, this search demands more patience than almost any scientific endeavor in history. Think of how slowly the evidence accumulates. One rover finds a clay deposit, a sign that water once lingered there. Another discovers complex salts that can preserve moisture. A third detects methane that fluctuates with the seasons. None of these findings alone is proof, but together they build a circumstantial case, a mosaic of possibility that draws us onward. And perhaps that is the real power of Mars as a symbol. It is not only a place we can see and measure, it is a mirror for our own hopes, our need to believe that life is a common story, not a lonely accident. Some critics argue that this is romantic nonsense, that we project our longing onto a lifeless desert. But even if we never find a single microbe, even if Mars proves utterly sterile, the search itself transforms us. It forces us to refine our methods, to ask better questions, to invent technologies that can one day carry us further. And in that process, we become something more than we were. We become a species willing to look beyond the comfort of the familiar, willing to spend decades decoding the quiet testimony of an ancient landscape. So when you see the next photograph from Mars, a ridge under the pastel sky, a wheel track etched in dust, remember that you are not simply looking at scenery. You are witnessing a fragment of an unfinished investigation, a clue in the longest detective story ever attempted. As we follow this trail of clues across the Martian surface, it's tempting to imagine that discovery is only a matter of collecting enough evidence, that sooner or later a single experiment or photograph will deliver the final, incontrovertible answer. But in reality, exploration rarely works this way. It is a process defined less by dramatic breakthroughs than by incremental insights, small revelations that shift our perspective 1 degree at a time. And sometimes the most significant discoveries are not about what we find, but about what we learn to see differently. Think for a moment about how many times humanity has misinterpreted distant worlds. When early astronomers observed the moon through primitive telescopes, they mistook shadows for mountains, bright regions for continents, and imagined oceans where there were none. Later, the first blurry images of Mars led generations of scientists and dreamers to believe in a network of artificial canals. Even now, with spacecraft capturing gigabytes of precise data every day, we are not immune to illusion. This is one reason planetary science demands humility. It reminds us that perception is not a neutral act. It is shaped by expectations, shaped by the way our minds look for patterns, even when none exist. Consider the most famous example of this: the face on Mars. In 1976, NASA's Viking 1 orbiter photographed a mesa in the Cydonia region that, from a particular angle, appeared to have eyes, a nose, and a mouth. Newspapers announced it as evidence of ancient Martian architecture. Some insisted it was a deliberate monument carved by a long-vanished civilization. For decades, the face became a symbol of our yearning to find ourselves reflected in the unknown. But when higher-resolution images finally arrived, the illusion dissolved. The face was nothing more than light and shadow playing across an ordinary hill. There were no ruins, no inscriptions, just rock shaped by erosion. Yet even after this debunking, the legend persisted because the story was more seductive than the reality. We might smile at such misunderstandings, but they reveal something profound about how we approach the universe. Our instruments can extend our senses across millions of kilometers, but they cannot remove our biases. Even the best cameras, the most advanced sensors, still require interpretation, and that is where human subjectivity enters. Every photograph is a collaboration between fact and imagination. This is why scientists are trained to be skeptical of first impressions. When an unusual feature appears, whether it's a bright streak, a geometric shape, or a transient shadow, researchers ask, is this a genuine structure, a trick of the angle, an artifact of the sensor, or perhaps something even stranger, an unrecognized process, a phenomenon never before recorded? It is an essential discipline, the willingness to doubt what seems obvious, to test every hypothesis against evidence, to accept that sometimes the simplest explanation is the correct one. Yet in this discipline, there is also an undercurrent of wonder. because every illusion that dissolves leaves behind a deeper truth. That reality is more subtle than any fantasy we impose upon it. And sometimes, when the illusions fade, what remains is even more beautiful, a landscape shaped by time and physics alone, unmarked by intention, yet still worthy of our fascination. So, when we examine the next image from Mars or the Moon, when we trace the contours of an ambiguous shadow or a curious ridge, we are not just searching for confirmation of old stories. We are practicing a kind of intellectual courage, the courage to let go of cherished beliefs in exchange for understanding. And in that practice, in that commitment to seeing clearly, we honor the most powerful tradition of exploration, to prefer truth over comfort, even when the truth is harder to accept. But there is another side to this discipline, a quieter dimension that is just as essential to exploration: the capacity to wonder, even when certainty is out of reach. Because in the end, the most valuable discoveries are not always the ones that answer our questions, but the ones that invite us to ask better ones. You can see this in the way scientists respond to the unexpected. When the first high-resolution images of Mars revealed the recurring slope, lineae, the dark streaks that appeared and disappeared with the seasons, the immediate instinct was to interpret them as water flows. The patterns looked so familiar: channels descending steep slopes, tapering into fans at the bottom. On Earth, no one would hesitate to call them evidence of liquid movement. But Mars is not Earth. Its atmosphere is almost a vacuum. Its temperatures plunge far below the freezing point of water. And so, even as the images accumulated, so did the contradictions. Some experiments suggested that briny water could persist under certain conditions, but others showed that granular flows of dust could create identical shapes. Every hypothesis raised new questions. How much salt is needed to keep water liquid? What triggers the flows in the first place? Could they be driven by sublimation or even by the impact of tiny meteorites disturbing the surface? It would have been easier to choose the most satisfying explanation and move on, to declare, once and for all, that Mars still hosts seasonal trickles of liquid water. But science is not built on satisfaction. It is built on patience, on the willingness to remain in uncertainty for as long as necessary, and to resist the temptation to confuse plausibility with proof. This is not a glamorous process. It does not lend itself to headlines or viral excitement, but it is the heart of exploration. To admit what we don't know, to refine our models, to build new instruments capable of resolving the ambiguity, and to accept that sometimes the best we can do is to narrow the possibilities rather than declare a final answer. If you think about it, this commitment to nuance is a kind of moral stance. It says that truth matters more than reassurance. That complexity is not something to be feared, but something to be respected. And in an era when information moves faster than reflection, that stance feels almost revolutionary. Yet, for all its rigor, science also leaves room for imagination. Because the fact that we have not yet proven the existence of liquid water on Mars does not mean we have proven its absence. The evidence remains tantalizingly balanced, two competing hypotheses, each supported by partial clues. And somewhere in that balance is the possibility that we are still on the verge of discovery. This is why missions to Mars continue. Each new rover carries instruments designed to weigh the scales, spectrometers that can detect hydrated salts, cameras that can monitor subtle changes in albedo, drills that can extract samples from just below the surface. We are building the tools we need to move from speculation to evidence. And while we wait for those results, we are learning something profound about ourselves. We are learning that curiosity is not a weakness, that uncertainty is not failure, and that the willingness to question is the most powerful engine of progress humanity has ever created. Because when you stand on the edge of the unknown, whether it's a Martian crater, a lunar mascon, or the searing corona of the sun, what you feel is not just the thrill of discovery. You feel the humility of realizing that the universe does not exist to satisfy our expectations. It exists on its own terms. And if we are wise, we will meet it with open eyes and an open mind, prepared to be surprised again and again. As we turn our gaze from Mars back toward the Moon, we find ourselves confronting a paradox that defines so much of planetary science, that the closer we look, the more elusive certainty becomes. For a body that seems so familiar, so unchanging in our night sky, the Moon remains a place of profound mystery. And no mystery is more compelling than what lies beneath its surface. It's strange to think that after more than 50 years of exploration, we still don't know exactly how the Moon is structured inside. We have models, elegant simulations that combine seismic data, gravitational anomalies, and magnetic readings, but no direct measurements below a shallow crust. The deepest cores ever drilled by astronauts or robotic landers barely penetrated a few meters into the regolith. Beneath that fragile skin lies a world we have never touched. Consider what we have learned so far. The Apollo seismometers left on the near side recorded thousands of moonquakes, some triggered by tidal forces as Earth's gravity squeezed and stretched the lunar interior, some caused by meteorite impacts, and some by the slow contraction of the cooling mantle. These seismic waves told us that the Moon has a layered structure, a crust of fractured rock, a mantle that may still be partially molten in places, and a small metallic core that holds clues about how the Moon formed. Yet, even those signals left puzzles unresolved. For instance, why is the crust so much thicker on the far side? What accounts for the mascons, those buried concentrations of dense rock that tug on spacecraft as they orbit? And how did the near-side basins fill with dark basalt while the far side remained mostly highland? One hypothesis suggests that the early Earth, still red-hot after the impact that created the Moon, radiated so much heat onto the near side that it slowed the cooling of that hemisphere, allowing lava to well up through thinner crust for longer periods. Over time, this created the vast Maria we see today, mottled expanses of cooled basalt that give the Moon its familiar face. Meanwhile, the far side cooled more quickly, retaining a thicker shell of ancient crust, more resistant to volcanic resurfacing. But even this theory is incomplete. It doesn't fully explain the distribution of radioactive elements or the curious pattern of gravity anomalies that Grail mapped in such exquisite detail. It doesn't tell us whether the Moon still hides pockets of magma or whether its metallic core is completely solid. This is why the next generation of lunar missions will be so transformative. For the first time, landers and rovers will carry deep penetration drills capable of sampling rock tens of meters below the surface. New seismometers will be deployed on the far side to complement the data from Apollo. And orbiters will continue to refine gravity and magnetic field maps, looking for subtle clues that might reveal the Moon's hidden history. But there is more than scientific curiosity driving this return. There is also a growing recognition that the Moon could become a proving ground for technologies we will one day take to Mars and beyond. Learning to build habitats in low gravity, to extract water ice from shadowed craters, to generate power from sunlight and radioisotopes. These are not just technical challenges. They are essential steps toward becoming an interplanetary species. And perhaps this is why the Moon still matters so deeply. Because in its pitted surface and silent valleys, we see the record of our own origins. We see a laboratory where the rules of planetary evolution have been written in rock and dust, unblurred by atmosphere or erosion. And we see a place close enough to reach, a place where humans can stand and work and build and learn. So the next time you look up at the Moon and trace the familiar outlines of the Maria and Highlands, remember that you are looking at a world still unexplored in its deepest layers, a world waiting to be understood not only through telescopes and robots, but through the direct presence of human curiosity. Because when we finally return, not for brief visits, but to stay, we will be carrying more than instruments. We will be carrying questions older than our species, questions that only the moon itself can answer. And as we imagine those future explorers stepping onto the lunar regolith, we're reminded that the moon is not merely a backdrop for our ambitions, it is a place that will test every assumption we hold about survival beyond Earth. Because unlike Mars, with its thin whisper of atmosphere and faint promise of seasonal change, the moon offers no illusions of habitability. It is a world stripped to its essentials: rock, dust, silence. That silence is perhaps its most haunting quality. On the moon, there is no air to carry sound, no wind to rustle dust across the plains. When an astronaut moves, the only noise is the muffled thump of boots transmitted through a spacesuit. When a tool strikes rock, the vibration travels up the glove but never escapes into the vacuum. Imagine what it must feel like to stand in such a place, to know that you are alone in a way no one has ever been alone on Earth. Yet even here, in this quiet desolation, we have found traces of dynamic processes. The slow migration of regolith stirred by micrometeorites over billions of years. The constant bombardment by cosmic rays and solar wind, which slowly alters the chemistry of the surface. The faint seismic shivers that ripple through the crust when the moon passes closest to Earth. This is not a dead world. It is a world in a kind of suspended animation, preserving in exquisite detail the record of its own formation. And there is more. In the deepest shadows of polar craters, places where the sun never rises, scientists have detected reservoirs of water ice, cold-trapped over eons. These deposits are not just a curiosity. They are a resource, perhaps the most valuable one in all of near-Earth space. Because ice can be turned into drinking water, it can be split into oxygen for breathing and hydrogen for fuel. In a future where human presence becomes permanent, these hidden caches may be the key to unlocking the moon as a staging ground for voyages farther out. Consider the implications. If we can learn to harvest lunar ice, to build life support systems that function indefinitely, to construct habitats shielded from radiation and thermal extremes, we will have proven to ourselves that Earth is not the only place where humanity can survive. The moon becomes not just a destination, but a crucible, a place where the technologies of interplanetary civilization are forged. Yet, none of this will be easy. The moon's surface swings from blistering heat to deadly cold every 2 weeks. Dust is not merely a nuisance, it is a hazard, sharp, electrostatically charged, and capable of infiltrating every seal and joint. The vacuum corrodes materials in ways unfamiliar to terrestrial engineers. Even the gravity, at 1/6 of Earth's, will challenge our biology in ways we have only begun to study. And still, we will go. Because in that going, we affirm something about our nature. We are not content to be confined to one planet. We are not satisfied to learn only by remote observation. We need to be there, to touch, to build, to test, to adapt, to leave our footprints in the dust and, in doing so, to claim our place in a much larger story. This is why the moon has never lost its hold on our imagination. It is close enough to reach with today's rockets, but distant enough to feel like another world. A place that reminds us how thin the line is between the known and the unknown. And when the first long-duration lunar habitats rise on the rim of a crater, gleaming modules catching the unfiltered sunlight, we will look back on these early observations, these decades of patient mapping and remote sensing, and understand them for what they were: the prologue to a new chapter in human history. A chapter in which we learn for the first time how to thrive in the silence of space. As we stand on the threshold of this next chapter, one that will carry us from Earth's orbit to the moon, to Mars and beyond, it is worth pausing to consider what truly drives us. Because exploration, at its heart, is not about conquest or even discovery alone. It is about perspective, about the way the act of going changes who we are. When we first launched cameras to orbit the moon, we thought we would find confirmation of our expectations. smooth plains perhaps, or predictable craters. Instead, we found the opposite. A landscape wilder than we imagined. Gravity fields so uneven they could yank a spacecraft out of orbit. Subtle variations in heat and composition that told a story more complex than any myth. When we sent our first orbiters to Mars, we believed we were leaving behind centuries of fantasy, canals, civilizations, great cities of stone, and in a way, we were. But what we discovered in their place was not disappointment. It was something more profound, a record of rivers that once flowed across deserts, a testament to a planet that changed, froze, and persisted. We found not the echo of a lost empire, but the possibility that life, simple, tenacious life, might once have taken hold in those vanished lakes. And when we pointed our instruments toward the sun, expecting to measure predictable cycles, we found eruptions of energy so vast they could scorch a planet. We found corona hotter than their source, magnetic fields twisting and snapping with a power beyond our scale. We found, in other words, a reminder that even the most familiar presence in our sky is still a frontier. In all these places, in the quiet plains of the moon, the rust-colored gullies of Mars, the searing brilliance of the sun, we have learned a lesson that no instrument can fully quantify. That certainty is temporary, that understanding is a process, and that wonder is the fuel that sustains it. If you close your eyes and imagine the future, say 100 years from now, you might see the outlines of what our curiosity will build. Lunar bases clustered around the poles, harvesting ice to sustain life. Martian greenhouses glowing faintly under an ochre sky. Solar observatories stationed in deep space, mapping the sun's moods in real time to protect the infrastructure of an interplanetary civilization. But even then, even with all the technology we can imagine, there will still be questions no algorithm can answer. What does it mean to stand on another world and look back at Earth, reduced to a pale point of light? What does it mean to understand that, for all our divisions, every human being is bound to that fragile sphere? And what does it mean to know that the cosmos is not here to answer our fears, but to ask us to grow beyond them? Because if exploration teaches us anything, it is that our reach exceeds our grasp, and that this is exactly as it should be. The moment we believe we have nothing left to learn is the moment we stop becoming more than we were. So let us keep asking. Let us keep sending our instruments, our robots, our questions into the darkness. Let us keep building telescopes to peel back the glare of the sun, orbiters to scan the hidden side of the moon, rovers to follow the trails of vanished water across Martian craters. Let us never grow tired of seeking. And in those rare moments when a photograph returns that defies explanation, a shape that looks like a colossal bird spreading wings over the corona, a slope stained by a pattern that no model predicts, a ridge that disappears under better light, let us remember that these are not failures of understanding. They are invitations, reminders that the universe is not obliged to be simple, that it is, in the end, richer than any story we tell about it. If you feel small when you look up at the night sky, know that you are not alone. We all feel it. But in that smallness, there is also a kind of freedom, a realization that there is no limit to the questions we can ask or the horizons we can approach. This is why we explore, not because we expect to find answers that will end all questions, but because we hope always to find better questions, and to become, in asking them, something more than we were before.